This is Maria Patterson. I'm going to tell you today about my research this summer on database performance assessment for data curation of the VVD survey. First of all, I just want to thank the Open Science Data Cloud for funding this project for me for the summertime. I learned a lot. I also want to thank the people at the University of Edinburgh Informatics, in particular Oraklis Klapanos, who worked very closely with me, Malcolm Atkinson, and the Data Intensive Research Group, and Ross Collins, Nick Cross, Mark Holloman, and Bob Mann at the Royal Observatory, Edinburgh. So to introduce this topic, I should first tell you a little bit about why databasing is important for astronomical surveys. The success of large astronomical sky surveys, such as the Sloan Digital Sky Survey, has revolutionized data collection in observational astronomy. Small-scale telescope observations performed by individual astronomers are becoming increasingly less common in favor of dedicated surveys producing massive data sets. So astronomers now are becoming less limited by the availability of data, but by the ability to quickly and easily handle large data sets and perform their analysis. To do this research project, we took data from the VISTA variables in the Via Lactea survey, which is a survey towards the center of the Milky Way that looks for variable stars. So what it does is the telescope looks at the sky over and over again, taking images in the same place over different nights to search for stars that are changing in brightness or position. So this is the largest survey that's part of VISTA, Visible and Infrared Survey Telescope for Astronomy. The detection table itself, which is only part of their data, has 3 times 10 to the 10 rows of detections currently, growing to 1 times 10 to the 11, with 132 columns of different attributes such as brightness and position. Currently the data is so unwieldy that this detection table is split horizontally by month and vertically into 3 subtables. In order to help solve this problem of this very large data table, we experimented with a different database management system, MonadDB. And MonadDB is different from MSSQL in that MSSQL server is a row-oriented database, while MonadDB is a column-oriented database. To compare the two, we took the same data set and we ran the exact same SQL queries on the two databases, giving them each identical hardware configurations. So we have 2 different operating systems, Windows Server 2008 for MSSQL server and Debian Linux Jessie for MonadDB. Each of them is given 1 physical disk, 12 cores, 12 gigabytes of memory, and 6 terabytes of disk space. Our plan was to look at 2 tables, a small detection table with 10 to the 7 rows, and a larger detection table of 5 times 10 to the 8 rows, but unfortunately, due to some disk and VM failures, we were unable to complete anything for the larger data set, so that's something that's still ongoing. What we did to compare the performance of the 2 databases on the different queries, we wrote mmonitor, which is a Python code that monitors the following information during each query task, using Python's psutil, which is a cross-platform process and system utilities module, which we needed because we were working on a virtual machine on Windows and a virtual machine on Linux, and we wanted to be able to compare them equivalently. So we pull, throughout the duration of any task, system statistics such as CPU utilization and disk I/O statistics, and also different process statistics for every instance that the database is running a server to complete the task. And what we did was monitor 3 types of tasks that are commonly used in astronomical data curation and are being used by the VVV survey. The first one was to bulk insert a whole data table using the small detection table of 10 to the 7 rows. The second one is to insert new rows of data into that data table and then update sequential IDs into the table, which is the column update, and C, to update whole columns, which you might do if you're recalibrating the photometry, which is the brightness, or the astrometry. So I'll just show you a couple of graphs for two of the tasks that we ran. So task A, this is bulk loading the whole tables. This is for the small data set, 10 million rows, and 130 some columns. This is 12 gigabytes of data. If you do this on MS SQL Server, shown on the left, it takes 78 minutes, and on the right in red is MonadDB, and it's only 8.7 minutes. So here we're showing the bytes read, bytes written, process CPU, and system CPU that's going on during the execution of this task. And it seems as though MonadDB has just kind of figured out a more efficient way to do this by not having to read any information while it is loading the whole data table, and it waits to the end to make sure to check all of its constraints. So it's much more efficient. In our second task, inserting new rows into a data table. So we insert basically half of the table. We delete half the table, and then we insert those rows back in. Here, MS SQL Server takes 13.1 minutes, and MonadDB takes 6.9 minutes. Again, it seems to be more efficient in the way it's doing things. It reads through the table first, and then checks all the constraints and writes what it needs to afterwards, instead of continuously throughout the task. And then here is the second part. So after you insert new data rows, you have to update the ID column to make sure that they're sequential. And so in MS SQL Server, this takes 1.25 minutes. And in MonadDB, this only takes 2 seconds. So this is really what MonadDB was sort of meant for, is to do these column updates. So here it is particularly much faster and more efficient than MS SQL Server. A reflection for this summer of what we were able to achieve is we wrote and implemented a system monitoring tool that works on any command line executable over the duration of a task. Compared MS SQL and MonadDB for a data subset from the VVV survey to find that MonadDB outperforms MS SQL in 3 common Astro curation tasks. Some key difficulties that we encountered: several virtual machine and disk failures, which kind of kept us from moving forward to the larger data sets, and realizing that recovering and moving large data sets takes up a large amount of time. There's still, of course, remaining work to do that can be continued. We can compare the performance of these two databases with a larger data set with more rows that don't fit into memory, and we can do additional tasks such as joins with other tables, because this was only one table that we were looking at the moment. That's it. Thank you for listening.